paper thing produces anxiety attacks in you. So I brought with me some 5 examples from previous term papers. These students did not give me the permission to actually even show them to you, but I don't think they mind, particularly because I did not bring quote-unquote poor term papers. That they may mind, even though maybe they would have been better examples. So these are all letter grade A papers. All right. So feel free to look at CSP. And today we are going to begin with the so-called asynchronous message passing. So let's summarize what we have done here. Before we go into that, there were a few term paper topics that I did not agree to, as you all know by now. They need to turn in the replacement titles by Friday morning. And since we don't want to go through another round of rejection, etc., whatever you're about to turn in on Friday morning, you talk to me prior to that, so that they don't go through some more. And then I'll post the revised list. So far, what we did in CSP is what is known as synchronous message passing. We had the input-output events in different processes be viewed as the same event overall. And so we have this 2-aspect primitive that you may have studied before are now very coupled here. That a process wants to communicate to another process what it has computed, as well as that these two are waiting for something to happen and only then they will proceed. These two activities, communication and synchronization, appear in the CSP notation as coupled, inseparable items. Okay. And on the other hand, and this is going to be hard for you to believe at this moment probably, that this is a practical thing. This is what is more doable in terms of hardware, actual electronic hardware. And hence it is much more realistic, this synchronous message passing. And just to be sure, I thought I would explain this idea again in terms of a more formal rule, which is this. By now you should all understand what that means, right? Right, the bottom 2 lines are saying that once the thing happens, once the input-output occurs, it is almost like an assignment statement. Okay. And the rest of the stuff is all detailed, and we'll look at that in your book. Now let's look at what we mean by asynchronous message passing. Well, in this case, we are decoupling the 2 things that we had inseparable in the previous way of doing things. Now, we're only talking about communication. That is, somebody sends and the sender does not get lost at all, no matter what. And so, this implies that, effectively speaking, regardless of who does this implies infinite amount of buffer. Somebody has to be able to hold a large number of messages because they have been sent, but they have not been received by anybody. On the other hand, of course, a receiver does not get a message if there is nothing there in the buffer pool. So obviously, there is a potential delay for the receiver, but never a delay for the sender. So receiver waits for something to become non-empty, some particular channel. We'll use this word in a more aggressive way. So if you look at the two processes A and B, there is some kind of a connection there, and depending on this connection, we refer to this message passing as either synchronous or not. And already in the case of asynchronous, we have therefore assuming these two things. There is no synchronization implied from sender to receiver. On the other hand, there is an implication of infinite buffering. And yet, on the basis of these two operations, we cannot arrive at good algorithms unless we make further assumptions. For example, even though we are saying here, send E to process B, and process B receives this message in a variable called X, we still need to talk about in what way does this infinite buffering occur. It is possible that things are put in there out of order, not necessarily based on the order in which they are sent. And it is this kind of stuff that we'll be talking about in the next few minutes, certainly probably the whole lecture today. And in order to do that, we need to understand the so-called happened before relation. Some of you may have seen this before. So let us recap this. Is it true or not? All of you have seen this before. Some of you have not. Okay. Here the letters ABC are not processes. These are events. And what is an event? Well, anything you care to call an event is an event. So we don't care what the definition is. In particular, the assignment statement, the execution of the assignment statement is an event. Or sending something is an event. Receiving something is an event. Okay? So it doesn't really matter what is called an event. So ABC are events. Things that have happened at certain moments in time in various processes. Not necessarily in the same process. The A, B, C, those three things may have happened in different processes. Okay? Given that, we expect one of these three things to hold. So if you look at two events, A and B, we want to be able to say either A happened before B or otherwise. Right? Makes sense. A happened before B. If that's not the case, B happened before A, or else they happened at exactly the same time, so to speak. Right? And so that is our overall goal. Overall goal that we have for these events is that one of these three holds. And the arrow is to be read as happened before. Okay, but for now intuitively understand what we mean by happened before. So if I write A arrow B, that means I'm claiming that A occurred or happened before B did. Okay? And we will soon raise the question that this is not always easy to answer. But assuming that it is easy to answer, you know what we mean. This is a relation, it is either going to be true or not. Okay? So, we expect one of these three things to hold. And our problem is, how do we decide that? Given A, B, C, how do I decide whether A happened before B? Since there is nothing specific about A and B, the reverse question is the same. B happened before A is not different from this. So we want to know if A happened before B, or is it the case that A and B are concurrent? Okay? And for the time being, keep a completely open mind about the word concurrent. Okay? Here comes yet another meaning of the word concurrent. Well, there are some obvious cases where the answer is clear. Suppose A and B are events in the same process. Remember, I did not say so far that they are. But suppose they are. Then, suppose A was executed before B. Now this is one process. So this is clear, right? That A got executed before B. You should be able to tell that A was or was not executed before B. Given that they are in the same process, you know the answer. And if that is the case, it's clear that A happened before B. Okay? So this one is easy. On the other hand, suppose A is the event of sending something from a certain process. Then B, suppose, is the event of receiving that message, and is important. That message, which was sent. Right? And I think now you agree that we should have something relating to physics here that should be valid. You cannot receive something unless it is sent. Right? Otherwise, this is not a safe system. Remember the safety definition. So, it should be the case that the sending activity occurred prior to the receiving. Even though send is done by one process, receive is done by another process. Right? So, in this case again, it is clear that A happened before B. On the other hand, maybe directly comparing A and B, you're not able to answer this, whether A is before B or not. But you are able to find a third event, C, such that it fits between these two. Then obviously A happened before B. Okay. So if any of these three hold, we have an answer to A happened before B. Okay. We still haven't said what we will do if none of these three questions yield the answer. Well, in which case, we will claim that A and B are concurrent. So, if you cannot say that A happened before B, or that B happened before A, then we will assume that they are concurrent. Okay? And probably a picture of some of these things would be helpful. You may want to take this diagram down. It is not from your book. Here, I'm showing you the time traces of three processes, P, Q, and R. Alright, I'll give you a minute to draw this. Okay, you are done. All the black arrows are obvious. It's the green ones that we should concentrate on. Suppose we ask the question, has P1 occur before Q3? What do you think? P1 and Q3 are clearly events in two different processes. And we answer that yes, because if you look at Q3, there is a Q2 that has happened before Q3. And the arrows across the processes are indicating send receives. Okay. So there is a happened before relation between P1 and Q2. And since this is our C, and these two are our A and B, and there exists a third one that fits in between, we claim that P1 happened before Q3. Okay? And similarly for Q1 and R1. Okay? This Q1 and this R1. Okay? Whereas if you look at P2 and Q4, we cannot find anything that fits in between. The two events are circled in red. P2 and Q4. Okay, therefore, P2 and Q4 are concurrent. Note that the scaling of the picture is fairly carefully chosen, deliberately chosen. It's in terms of the process P. P2 happened almost right after P1. And Q4 happened at several moments later than Q2. And even assuming a rather slow network, it is possible that Q2 happened within moments after P1. So it's very reasonable to actually observe in a real system that P2, if you were globally examining these three processes, you may actually find that P2 really did occur before Q4. But so far as this relation is concerned, that is immaterial. So far as this relation, as we know, is defined. Q4 and P2 are unordered with respect to each other. And so we say that they are concurrent. Okay? We're clear on this? Now, we can talk about the following way of producing and ordering on all the events so that our artificial expectations are met. Okay. This, first of all, we need to understand a little bit about the context also. We are now talking about distributed processes, distributed computers. So we are not assuming that all the machines are in one place. They are spatially distributed. One here, one in another building, one in another town, or even another country. So it is not a given thing anymore that they all have access to a central clock. So there is no global wall clock or any other kind of clock. If they need to know the time of day, they need to ask each other. So we are no longer able to use a central clock to say when a particular event occurred. If that was the case, if we did have a central clock, the previous problem was trivial. You just asked when did these events occur. So, in the face of non-existence of such a central clock, we still want to be able to say whether or not certain event happened before another based on some simple tests. And for that purpose, we are inventing a thing known as logical clock. So this serves the typical purpose of a clock, but other than that, it's not a clock in any sense. Okay? So it's not an intuitive ticking kind of clock. It's a clock that's going to tick tock in a very crazy way. Okay? So it's just a number. And we are going to have a number in every process of this kind. So each process has its own logical clock. I is the identity of the process. Okay. Now, every time an event occurs in that process will increment LCI. Increments it by 1. Okay. So that's clear enough. On the other hand, what is it that we want? We want to be able to do this. Given arbitrary events A and B, from the same process or from different processes, we want to be able to tell if A happened before B or not. And it's our goal to answer that question by looking at a timestamp, a logical kind of timestamp of A and B. If the logical timestamp on A is less than the logical timestamp of B, then we are going to say A precedes B. A happens before B.
Suppose that A is on a unit that, and it takes 1 year to complete this event, and B is on a cray and it takes 1 millisecond. So A starts before B, but finishes well after.
Well, you see, then it's a question of what you mean by event A finished. See, so far as this calculus is concerned, how long does it take for an event A to begin and end is material to us.
The timestamps are the end of the event, right?
In a sense. A at the end of A compared to the beginning of B.
End of A compared to
Beginning of B. We are not concerned with the duration of these two events, A and B. Again, there is no loss of generality in what we just said. The rest of it can be modeled in terms of what we just said. So in other words, we are pretty much assuming that the events A and B are instantaneous events. And with that, you can model any other long computational task with this. In any case, if you want, assume that we are beginning from the end of A compared to the beginning of B. Okay. So we want to be able to say A, we will say A happened before B if the timestamp of A is less than the timestamp of B. This is our goal. And in order to do that, we are now going to do this. Every time we are sending a message M, we will automatically append to that message the timestamp T. Now what's the timestamp? Well, this is the logical clock value that you have. So you being this I process, if you are sending the message M, you also send your value of LCI at that time. Okay? On the other hand, if you are receiving a message M from some process with a timestamp of T, now that's the time at which the sender sent it. Okay? And then you look at your own logical clock. Your logical clock is less than, ignore the equals. Seems to confuse things all. If it is less than T, okay, what has happened here? Somebody sent you a message at 10 a.m. And you look at your wristwatch and it says 9:30. And this is unreasonable. You cannot receive it before it was sent. So all that it means is that your clock is running slow. So we simply bump it up to 10:01. Alright, this is the idea of the thing. Let's first understand the idea before we question it. Alright, is the idea clear? Somebody sends you something at 10. You look at your clock. It says 9:30. Since he sent it at 10, and it takes a certain finite amount of time to travel this message, you agree to reset your clock. And of course everybody is agreeing in our system. So when you then send something back to the same sender, let's say, that sender may have to also do this. Alright? Are we clear on the idea here? And let's not worry about the case when these two are indeed equal. As my original slide had, even if it is equal, you want to bump it. But don't worry about that exceptional case. Yeah. Now question.
What happens if we have two messages with the same timestamp?
Okay.
And also the two timestamps is.
But remember, we are only receiving one message at a time. The sending and receiving are events. And just a while ago we agreed that events are instantaneous events. So we are not receiving two messages at the same quote-unquote time, during the same elapsed of time. These are to be thought of as momentary things, all these points.
We shouldn't think of the times as actual clock times.
No, that is why these are logical clocks.
So they're really more like a sequence number than an actual
Right.
time.
Right. But the technical literature uses this word, logical clocks. These are indeed sequence numbers, with a lot of numbers missing in between.
So in our scheme, are we allowing for a process to send a message to another process that's on the same physical box within this?
Right. We don't care where these are located.
So it doesn't matter that the boxes are distributed or not distributed?
Correct. As long as their primitives are send, receive. And in fact, that is going to be our almost final definition of what is distributed computing. It is distributed computing if the primary mechanism of communication is send, receive. Then you have varieties of send, receives. As we saw in CSV, and later on we'll go back to it again. Synchronous message passing, and we are now doing asynchronous message passing. Any other questions with this? Okay, so quick quiz type of question. Why didn't we worry about this in CSV? Right? The send and receive occur at exactly the same moment. So therefore this problem doesn't arise. Okay, so now that we know the logical clocks, the first problem that we are going to solve is the following. We now want to do a version of semaphores using these primitives. So far, we use the semaphores. We redefine carefully, and we basically said it's an abstract data type and that has these PV operations. Okay? Now, on the other hand, when two separate processes are doing an operation, either P or V, where is the semaphore S? In the same what? Well, before we achieve that. Well, see now we have two processes, P and Q. Let's not say P and A and B. And we are doing some P operation on some semaphore over here, and somewhere else down below we may do a V on S there. It doesn't matter in what order the P-V operations are occurring. My question to you now is, given that A and B together constitute, according to our definition so far, a distributed system, where is this S? Nowhere? No, it's not a logical plot. I mean, we'll use logical plots in a minute. But where is this S? Well, it doesn't belong, the important thing is, it doesn't belong to A nor to B. These two should somehow share this. We could, for the purpose of doing this, introduce a new process, and we did this once, if you remember in CSP. Introduce a third process, call it whatever, let's say SEM, which is the process that owns S and does the reasonable thing for P and B. And then A and B are sending things and receiving things from SEM, right? However, this is not a truly distributed solution. Why? SEM is a third process which has now become a master in a certain sense of A and B. It controls how A and B do it. And so this is not a so-called peer-to-peer solution. Here is a master-slave relation. SEM is the thing that is in control of this semaphore, and if something happens to SEM, the system will come to a halt. So this is also not false tolerance. Okay, now having said that, we are going to ignore that issue again completely. So our real objection is that this is a centralized solution. And as long as you are willing to have such a central process, such as SEM, of course you can use the old style technique to implement it. And you already saw that, how we do it in CSP. Now what we wish to do is, we wish to assume the non-existence of a central process of any kind. So we are going to now say all processes are quote-unquote alike. None of them have any extra privileges than any other. All of them are equally privileged. So if we have a bunch of these processes, A, B, C, D, etc., we want them to somehow communicate among themselves and arrive at an answer whenever they need to do a semaphore operation. So in other words, we are looking for a semaphore implementation that is distributed. Okay, are we clear on this? What we are talking about today? And we are going to try to do this using our asynchronous message passing. And we need a bit of notation. And again, this is straight from the textbook. We're going to use a thing known as channel. And this is really an abstraction of a real network, such as Ethernet or whatever. Okay. And the syntax for the send operation is going to be like that. Send. And now you are going to name a channel. This is much like in CSP you named the recipient's process. Here you are going to kind of name the pipe that it is connected to. Now this is not Unix pipe, but conduit. Okay, called a channel. And into that channel named CH, you will stuff the values of these expressions. E1 up to En. That is the send primitive. Okay? And for us, it is going to be an atomic primitive. So it cannot be stopped in between. So that we can pretend it is a simultaneous input. Okay, similarly, receive takes things out of that conduit, that conceptual pipe, and it gets n items from that, and it then assigns these n items to these variables, respectively. The thing that you sent as E1 then is given to V1, etc. Okay? So when these two are coupled, when these two occur in a matching way, then the effect is as if V1 is assigned E1, V2 is assigned E2, etc. simultaneously. Okay? That assignment is simultaneous. But you will see that we will never even use multiple repetitive names in the sequence. So it really doesn't matter. Okay? And we declare this name CH like so. Kind of like a variable. With field name I1 up to IN with types T1 up to Tn. Okay? And of course we have typical type matching rules. E1 should be of the type T1 and V1 should be a variable of type T1, etc. To recap, sender and receiver are of course acting independently. And a message may be received intuitively long after it was sent. Sending itself is atomic, receiving itself is atomic. But if you are observing the whole thing globally, sending may have happened 1 year ago and is yet to be received for whatever reason. On the other hand, and of course it's finite capacity. On the other hand, we are assuming that the order of sending equals the order of receiving. So they did not get jumbled up along the way. In a lot of real-life networks, that is not true. That order of sending equals order of receiving. For example, in the typical U.S. mail, this is not always true. Depending on the day you mail it may arrive sooner. Okay, so with this, we are about to solve the following problem, that of implementing semaphores in a strictly distributed way. Okay? So when you look at the next slide, which is directly from the textbook, question everything. Alright? And as usual, it may take a couple of passes after you are done, after we are done in the class today, to fully get it. So here is, this is 720. This is the algorithm, and, oh, don't take this down. It will take forever. But let's make some syntactic observations. The green stuff is what a process will do when it wants to do the equivalent of a V operation on a semaphore. Okay? So, in your high-level code, wherever you used the V operation before, you replace it with this green box whenever you want to do a V operation. Okay? Similarly, whenever you want to execute the T operation, you do the blue box. Alright? Now, all of this stuff for one semaphore. So if your algorithm requires 3 semaphores, you need to do this kind of thing 3 times. Alright? Furthermore, in order to explain this idea clearly, we are assuming, and reasonably, we are assuming that there are a fixed number of processes in our system, namely n. Alright? Small n. So this number won't go up or down. It will remain that way. Okay? And again, to explain this properly, we are assuming that each of these processes is kind of divided into two pieces. One that is the original process as you imagined it in the original coding. Again, in case you're lost in context here. We are now assuming that we have a certain distributed whatever using PD operations. And now we want to implement PD operations themselves and not given those. So your original process is your user process here. To each one of those, we are going to attach an associate called helper process. So if you originally had n processes, we now have n new helper processes. Alright? So altogether, in this sense, 2 n processes in the system. Originally, you didn't have any of the helpers. Originally, you had the user processes. The change that we made in the user processes is, wherever there was a V, we put this green box. Wherever there was a P, you put the blue box. Okay? Clear? Now, we have the following things. We have a certain number of channels called SEM-OP. How many channels? N of them. Okay? And each of these channels can receive a triplet. The first item is called the sender in the triplet. The second item is called kind. And the third item is called timestamp. All of these are integers. Okay? And then we have another n channels called go. That's the name of the array of channels. And these things simply contain one number that can be sent to that channel, which is the timestamp only. Okay? So how many channels do we have altogether? 2n channels. The first n channel is called SEM-OP. The second n channel is called go. Okay? Now these channels are global to all the 2n processes. Is this kosher? Huh? These are channels. Right? Agreed? So I'm not pulling a trick on you, right? Because these are channels, these are connecting 2 or more processes, the green stuff there. It would be incorrect to see any other global other than channels. Now, these variables, LC and TS here in the user process, those are strictly local to that user process. Okay? As in CSV, we are writing the code for the ith process. And all the n processes are identical, with the I replaced from a value from 1 to n. Alright? So, the LC gets initialized to 0 at the beginning of life, so to speak. And TS is our timestamp that we will use in the Go messages. And let's make the following other syntactic observations. If you look at the code carefully, you'll see that the Go is used exactly in 2 places. One is here and the other one is there. Okay? So, it is always the case that the user will be doing a receive on the Go and the helper will be doing a send on the Go. Alright? There's no other possibility here. And the user, the ith user process will be doing a receive operation on the ith Go channel, as you can see. Right? Go subscript I. And similarly, it is the ith helper which who will be doing the send on Go I. Alright? So now you can see the overall idea. The broadcast is exactly equivalent to doing a for loop with send inside. The broadcast sum of this is exactly the same as doing a send to all the channels named sum of. Okay? Are we clear on this? There are n sum of channels. To each one of them do a send of the triplet, I, P, and LC. This one. Okay? So broadcast is not a new primitive. Of course, we will not assume that broadcast is atomic. Each send is. But that appears inside the loop, so we cannot, we could make yet another assumption that the entire loop is atomic, but we are not. So, when a process wishes to do a pre-operation, what does it do? It sends these triplets. I is its own number, process ID so to speak. P is the kind of operation that it wants to do on the semaphore. LC is its own logical clock value. Remember, we are always going to send the logical clock that we have for all the dollar messages from now on. Okay. So LC is the timestamp of that message. And this is being broadcast by the ith process. Okay? So what it is saying is, it is saying to the rest of the community of processes, hey, I want to do a P operation. That's all it is saying. And it then, by its own discipline, wait to receive this message. This message it will receive on its own Go channel. Okay? So it's going to wait for something to appear on the ith Go channel. Alright? And what does it get? It gets one number on this channel. Right? You can see it from the declaration of TS. And following our rules about how to update logical clocks, it changes its own LC. Right? It receives TS, it sets it to the maximum of these two updating units, which is roughly the same. Right? Are we clear on this? So, you broadcast your intention of doing a P operation, and then you wait for something to appear on the ith Go. And when it appears, you update your logical clock, and this is effectively the completion of the P operation. So, whoever puts something out on the Go, ith Go, better be sure that this P operation is being done validly. Right? That task we haven't discussed yet. That is being done by the helper. Alright? Similarly, let's worry about what is it that we do for a P operation. In the case of a P operation, a process that wants to do a P operation, it simply broadcasts to the world, I am going to be doing a P operation. That's all it says. Doesn't wait for anything. And that being an event, it increments it by 1. It increments LT by 1, not the same. Okay? So are we clear on the specification of the user process, how we are implementing the PV operation? Once you understand this, think of an entire green box as a V, the entire blue box as P. Okay? Now, let's look at the helper processes. The helper processes are again written in the same way. This is the ith helper that is shown here. And there are n helpers. And each helper has its own local variables, these two. MQ is a queue data structure. Okay? And LC is its own logical clock. Nothing to do with the logical clock of the user process. Okay? And this SEM is going to simulate our original semaphore. But right now it is just an integer. Right? We do not have semaphores. So this semaphore is initialized to whatever you want your original semaphore to be at the beginning. Okay, so this is the initial value that you found for your semaphore. You plug that number there. And then onwards, we go into this non-terminating loop. Alright? So, how is this Q and Q maintained? Well, it is maintained in timestamp order. So it is not the case that things are only appended at the back and taken only at the front. They may have to be taken, they may have to be inserted in the middle of the queue depending on the timestamp value. And what does the queue contain at all times? It contains triplets. The first one is number, the second one is the kind of operation. They're either the P, the V, and you'll see a third one, ACK, acknowledge. One of these three enumerated values, followed by another number. So the Q, MQ, contains a sequence of triplets. Okay? We're clear on this? And we are going to assume that the queue is maintained automatically based on the timestamp order, which is the last number. Okay? So, let's see what it is that we do as a result of receiving some operation. Okay, in this case, this is the ith process, ith helper. Ith helper is listening to the ith semaphore, sema channel. Okay, it's not listening to any other sema channel. So it receives a triplet from the ith channel. Okay? Not clear? We are looking at that receipt. So let's see what happens when a user process did a V operation. It broadcasts to all the SEMOP channels, right? And let's say the process that wants to do the V operation is number 5. So all the helper processes got this. Right? All n of them got it. Sender will be what in that case? 5, right? And the K will be V. And TS will be the LC value that the sender sent. Alright? Clear enough? Now, depending on, well, and this is the normal updating of the logical clock. Depending on what this operation is, we may do one of these two things. Suppose it is a P operation. Well, in this case, we take this triplet, the sender, and the operation type, and the timestamp, and insert it into the queue. Of course, in the right place. Okay? Over there. And then, the helper does the following. The helper broadcasts an acknowledgement message. Okay? So it puts out an ACK message on all the SEMA channels. Remember, user processes are not doing a receive on semi. The user processes always do a send on semi. It is the helper process that does a receive on semi. Okay? So, in response to either a P or a V, what does the helper do? Simply takes this triple F, puts it into the queue at the right place. That's all. And then it does an acknowledge. Note that it sends this acknowledge not just to the sender. It's sent to the rest of the world, so to speak.
My question was, is the queue unique for each helper process? And then I
The MQ, yes. Yeah. This MQ, this LC, and this send, and this sender, K, and TS are all private to that helper. And even though the ith helper is kind of associated with the ith user, this LC is distinct from that LC. Okay, so this much is clear. Now let's see what happens when the type of the message you receive is ACK. Now who is sending ACK messages? Only the helper. The typical user process does not. The user process will only do PV. And by the same token, the user process, the helper process does not ever send PV messages. The helper process only sends ACK messages. Okay? It just follows from the text of the helper. So eventually, these messages that the helper process broadcasts, the ACK messages, the acknowledge messages, will be received by the helper process, right? Eventually. And at which point we need to do something. And this something depends on the idea of what is written here as fully acknowledged. And I'm going to explain that. But let's say you understand this roughly. Fully acknowledged means you got a response from all the processes, all the helper processes. Okay. This being the ith helper, it expects to get some kind of an answer from all the n-1. And it is only at that point it does something. In this case, it removes that message from MQ. Which message? The message that, the message that is fully acknowledged. Okay? What do we mean by this? Remember when we got the V message, we being the helper, what did we do? We sent a bunch of acknowledge, right? For that V message, how I got an okay answer from all the others? And if so, then I remove the V message from the MQ. Remember we inserted that over here. Okay? And similarly, if the message in question is a P operation, here is what we do. Here is the code for that. So we are looking at P messages that are fully acknowledged. We'll worry about the details of this in a minute, but roughly speaking, it means all the helpers say they have seen the acknowledgement that goes with this P. And furthermore, this ST stands for such that semaphore value as you are maintaining this sem, if it is greater than 0, then you do this. What is it that you're doing? Well, you're removing this message as before, and Now you are doing a send operation. To who? To the user process that you are coupled to. So it is your helper who will be on the lookout for you to tell you when it is that you can complete the P operation. There's silence in class. Yeah.
A while back you said fully acknowledged. You mentioned that there would be n-1 acknowledgements. I guess I'm a little bit confused.
N messages, because you will receive your own acknowledge. Sorry. N messages. Know that it is okay to send yourself things in this model. Why? Unlike CSP. In CSP, that's an immediate loss, right? You are stuck. In here, because of infinite buffering, the sender never locks. So you could certainly send it to yourself. Yeah, I should correct that. It is broadcast operation is for all the SEMOP channels. Now again, this I is not the index on which we are ranging from I to N. This I is a specific I, such as 6. This triplet, 6, ACK, and the present value of LC, is sent to all the N SEMOP channels. The same 6 will go to all the SEMOP channels. Okay? So I'll come back to this slide in just a moment, but let's look at what we mean by fully acknowledged. Straight from the book again. If you look at that queue, that queue has a bunch of messages stored in them. And let's look at a specific message M. That specific message M has a timestamp TS. Okay? And this is the front, that is the rear. The front is on the right-hand edge. Okay? So what can you say about the timestamps of these? The messages in front of M. Remember that we maintained it in timestamp order, so they're all lower, right? And if you now look at, this is the ith process from the perspective of one process, the one helper process, the ith one. Suppose we now can see somehow that this ith process has received a message. Ignore this part of the time. Suppose it has received a message from every other process, including itself. Again, that's not very well. Okay, suppose it has. Right? Is it something that you can tell? That you received, you being the ith process, you received a message from every process. How can you tell? Scan your MQ, look for first component, which will be the process ID of the sender, right? So you are looking for all the numbers. So it's easy enough to do. Okay? Now, that is not enough. You want to look for messages which have a timestamp greater than TS. Not only from all processes, but from each of these processes, you should have received a message with a timestamp greater than TS, where TS was the timestamp with the message M. Is it clear as to what we are looking for? Somebody sent us a message M. His timestamp was TS in the sending. And we are looking for messages from all processes with the timestamp greater than TS. And remember how we are maintaining the timestamp. How we are maintaining the logical blocks. Okay? Suppose this happened. Suppose we got these. Then we say that the message M is fully acknowledged. Intuitively, what is it that we are trying to do here? Well, when some process says it wants to do a P operation or a V, we tell it to all the helpers. By what? By ACK, right? And then we are wondering, when do we do this? Incrementing or decrementing operation on our SEM value. When everybody says, yeah, I have seen it. And that is what we are maintaining, we are determining by using this idea of fully acknowledged. Now, of course, the ACK message itself does not have to be inserted into MQ. It does not matter. Okay? So back to this slide. So, the SEM value is incremented here at the appropriate moment. This is decremented here at the appropriate moment. When is it appropriate to increment, let's say? You as a single user process wanted to do the operation. So you broadcast this thing. All the helpers see this. And they record your message in the queue. And then they send to all the helpers an acknowledgement. Right? Now, at this stage, what should happen? This value of LC is this value of LC, right? Which is indeed higher than TS. Okay? So, eventually these messages are going to be received by all the helpers, right? And where is it received? It is received here and K will be a CK. Correct? And now we record that another ACK has been seen. So we make a note of the sender who sent it, and we have the timestamp. And it is in this that we are talking about scanning the MQ, etc., to see if any message got fully acknowledged. So let us say we find some message M fully acknowledged. Okay? That message M is either a P message or a V message. And that is when we do either a decrement or increment. But in the case of a P message, we need to tell our companion to end his waiting. And the way we are accomplishing that is he agrees to do a receive as soon as he did a broadcast, and we agree to send him something. And we are the only one to send something to the IGO channel.
Yeah. Fully acknowledged the message. Does it really need to be the first beam message? If I'm the ICE process or ICE helper, and I send out a V message, or I should say I'm a user process, and I send out the V message, and then the helper sends out the acknowledgement. Does it really need to be the first acknowledgement?
No.
For a V message?
No.
Only for the P. Is that correct?
Yeah. In the case of the user process, as you can see, this is not waiting for any acknowledgement, but it needs its helper to receive it. for the correct updating of the same value. Again, in case this is unclear yet, note that the semaphore used in any solution is as if semaphore itself is a shared variable, right? Whatever semaphore S, let's say, if you do a PS and somebody else does a DS, what is this S? Conceptual. That's a shared variable. But this being a truly distributed solution, you cannot put this S in any common place. So who is maintaining the value, the numerical value of this S? Everybody. Each of your helper process has its own set value. So here is a puzzling question. Can you be sure that all of them have the same set value? What do you think? All of them have the same set value? Should they? At all times? Only in a certain quiescent state, when nothing is happening, or things have happened and now everything died down, so to speak, then you expect the same value to be the same in the entire helper system. But while send receives are in progress, in the sense that the channels are non-empty. If any of the channels are non-empty, this may not be the case. The send values in all the helper processes are alike, are equal. Now, this algorithm, as it is printed here on my slide and as it is printed in your book, has a typo. So don't ask your seniors, they'll find it. It's a confusing typo. So it's a good exercise to find the typo. The FA, in case I didn't say it, is abbreviation for all. Well, so here is the distributed semaphore algorithm. As you can see, it is certainly truly distributed. There are no shared variables across any two processes. They are all communicating using send receives. Now you can ask yourself, is this implementing a certain strong semaphore or a weak semaphore or what? What do you think? Offhand. Strong? What do you think? Now again, remember, in case you missed it, you do this per semaphore. So if you have 3 semaphores, you have 3 helper systems. Each helper system of n processes is accomplishing 1 semaphore and using 2 times n channels. Of course, in that sense, it is very inefficient. But this is a principle, of course. So in principle, to really implement the truly distributed semaphore, this is what it takes. All right, we will continue with this chapter. This is chapter 7. We'll be doing the next section following this one. have done so far.
No, I mean, still, when you say like,
Yes. Roughly speaking, the first 8 chapters of the book, constituting CSP is actually part of chapter 8.